All right, and we're back. So we're on day 2 of section 3.3. Now this is day 2 notes. We're going to do 2 days on day 2 because again, today's a short period. Today's class ends at 10:35, so we got about 20 minutes left. What did we learn yesterday? We learned yesterday how to identify whether something is linear or not, right? Based on a table, based on a graph, based on an equation. What we're going to do today is talk more word problems and say, how do we know if something is linear based on the context of a problem? That's what we're going to be looking at today. Now, what you're getting is a guy's notes and it's stapled together, and the only reason why it's a couple pages is because you have several word problems. Okay? Today, I'm hopefully going to get through the first word problem. I'm going to try to get to the second word problem, but we'll see. Oh, also, as I'm passing this out, just as a reminder, the grade that I just took a second ago was the last grade for the first 9 weeks. Everything past what I just checked is going to be on the second 9 weeks, okay? So everything past what I just checked just now is going to go on to the second 9 weeks. That means that it would be a good idea if you looked at Canvas, not just for my class, but for all classes, and made sure your grade is what you think it should be. Maybe you're looking back and you're like, wait, I thought I didn't miss any homework assignments. Oh, shoot, there's a 0 in for that. And then I look back, oh, I thought I submitted that. You need to go back through and look at those things, okay? And if the teacher allows you to, turn in late homeworks, that would be something that you should do before Friday, actually. All right. Linear functions, day 2. Now, what we're going to be looking at today is how we're going to actually start graphing. How do we create those lines? That's what we're going to be looking at. How do we create those linear functions? Now, the solution of a linear equation in 2 variables is an ordered pair. I give you input, it gives me back output. I choose an input value, I get an output value from it because it's a function. Every input has one and only one output. The graph of the linear function is just any and all coordinates that you could possibly graph. So anytime you see a straight line function on a graph, what you're actually looking at there is the infinite amount of coordinates that could be used to model that graph, model that equation. If a domain is continuous and I connect my line, then it's all the points in between there, right? All of those pieces in there could be a solution. Which brings me to my the key idea here. Now, I have been using these words. I have been using these words all along, ever since we started working with domain and range. So I think this should be familiar to us. The idea of a discrete domain versus the idea of a continuous domain. Discrete domain is a set of input values that consist of only particular numbers on a certain interval. Not all numbers on an interval, but only certain numbers on an interval. For example, they could be integers from 1 to 5. Now, what are integers? Integers are just positive or negative whole numbers. So if I only want integers from 1 to 5, that means 1.5 is not included in that set. That means 2.5, 3.5, 2.75, 1.25. Those numbers are not included in that set. The only numbers that are included in that set is 1, 2, 3, 4, and 5. Just 5 single solitary points. However, if I choose all numbers between 1 and 5, that means that's an infinite set. That means it's called continuous. A continuous domain is a set of input values that consist of all numbers along the interval. All numbers from 1 to 5. Any possible number from 1 to 5. That is more of a continuous domain. So, let's think about real-life examples of that. Well, for our discrete domain, we talked about number of apples, number of tickets. You can't go to the store and buy 1.5 apples. You can't buy 1.5 tickets to something. You can only have whole numbers, certain values, only discrete values. Continuous, that's more like I say, okay, I know a plant is going to grow 2 inches per hour, right? Is that growth only happening every hour? No. That growth is happening continuously. Even though I'm giving a rate per hour, that growth is happening continuously. It's happening at all points along the particular domain. Okay? Usually, time is continuous. Usually, time is continuous. If that's my input value, that is usually continuous. I don't want to say all the time, but it's usually continuous. So here's what we're looking at here. This is our first example. We got 4 word problems to do over the course of the next few days. Let's do one of them here. The linear function y is equal to 15.95x represents the cost y in dollars of x tickets purchased for a museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Okay, we've done this before. Let's do it again. Let's find the domain. Let's find the domain. Well, the domain of this function is all values that are acceptable that I could plug into that equation. What's the first value that I could plug into this equation? What's the first value?
1595.
No, plug in. Plug in. Let's get out. Let's plug in. What am I plugging in? What does that mean? What is my domain in terms of like example?
1.
1. That's the tickets, right? 1. That's my first domain, right? So it's 1. Can I plug in 1.5 tickets? No, that doesn't make sense. Next value 2. Next value 3. Next value 4. Can I do 5 tickets? No. Can I get, because I can do a maximum of 4 tickets. So I end it here. Now my range. Range, we'll talk about it. It only asks for find the domain of the function. But now we say, is that domain discrete or continuous? So what do I say? Discrete, because it's only single solitary points. There's no possibilities of any decimal values. So we would call it a discrete domain. And again, if I wanted to explain, the explanation to that is, okay, I cannot have any decimal values. Decimal values do not exist. It's only certain values between 1 and 4. Now, in the other examples, it asks me to identify what the pieces of the equation mean. So let's do that here. Y is equal to 15.95x. That's, I didn't take attendance first period. Uh-oh. Uh-oh, Mrs. Brown, did I not take attendance first period? Uh-oh. She was not here. Yep, bye.
I'll make my own little. It's a cupcake, but it's not finished. It's not finished.
All right, here we go. Sorry. And we're back. Okay, we talked about it is discrete domain, but now we say, let's ask this question. What does the 15.95 actually represent? What does that mean in the context? How much the purchase cost of each ticket? Good. Costs $15.95 per ticket. All right. Now what we're using is we're graphing the domain. Graph the function using its domain. So what do I need to do now? Well, if it's y is equal to 15.95x, I need to make myself a table of values. Okay, and we've got 1, 2, 3, and 4 using my domain. Well, just plug in. 1 times 1595 is 1595. and I've got 2, 3, 4 here. 2 is 3190. 3 is 4785. And 4 is 6380. All right. So those are my coordinate pairs. Now, what I need to do now is graph the function. Now, I'm going to, every time I ask you to do that, with exception to, oh no, I was going to say with exception on your homework, but I was nice enough on your worksheet on your homework to actually give you these graphs as well. But on your, every time you graph these things, every time you graph a function, and it's a real world problem, if it's a real life problem, it's a word problem, you need to label your axes. You need to explicitly define what your intervals are. What do I mean by that? Well, what does my x value represent again? What are my x values? The number of tickets. So we put that along the bottom. That's my independent variable. And remember, independent variable goes along the x-axis. What's my y-axis then? What's my dependent variable? Price, cost, right? Total cost. Okay, now I have to decide, am I going to use one box per unit?
No.
Probably not. Because think about my domain. I've only got 1, 2, 3, 4. So let's space them out a little bit. Let's say 1, 2, 3, 4. If you change the interval for the graph, you have to write it on there. If you change the interval for the graph, you have to write it on there. Henry, you should be doing this slowly. I'm not going to baby you. Do it. Now the cost. The cost. Okay, I've got to go from 0 all the way up to 6380. Maybe by fives. Let's see if fives make it all the way up. I go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. So that fits perfectly on my graph. Let's go by fives. So what I'm going to do is I'm going to make each 2 boxes, I'm going to make a 10. But make sure that you label that. I'm not going to be guessing at what your scale is. You have to label your scale. Every time you change it, you must label it as well. Now let's graph our points. 1, 1595. 2, 3190. 3, 4785. 4, 6380. Do we connect our dots?
No.
No, because this domain was discrete. Remember, we call this domain discrete, so therefore we do not connect our dots. Discrete domain does not get connected. Okay? Discrete domain is not connected.
It's not special.
Continuous domain is connected, but discrete domain is not. Why? Why is that the case? Well, because if I were to truly do this, now watch up here, please. You should not be doing this, but if I did connect my dots, what am I saying there? I'm saying there that this piece in here could possibly be a solution. Is 2.5 a possible solution? No. So therefore we say, no, we cannot have 2.5 tickets, so we should not have connected our dots. You only connect your dots when you have a continuous domain and not a discrete domain. You know, I'm not going to try to get into example 2, so I'm just going to leave because we only got 4 minutes left. Here's the deal. Here's the homework for tonight, and I'm just going to leave it on the front table tonight. I mean, it's due Friday. If you know you're busy tomorrow night, it might be a good idea to take it tonight and get it done. The front is everything that we learned yesterday. Look, there's some, is it linear or not? And then the back are the 2 word problems. And I gotta be honest, you could probably do these 2 word problems. We're just gonna do more examples tomorrow. We're gonna do 3 examples tomorrow, okay? So, I'm definitely gonna get this out to you tomorrow, but if you would like one tonight, you can have it. Please stay in your seats till the bell rings.